Okay, so now let's come to the overall matrix equation. Okay, so this whole thing is just going to be some number, right? So this will be some matrix, you can call it C, whatever, CPQ kind of a thing. Pardon me? Okay, so okay, let's rewrite this. So equation 1, okay, so equation 1 is going to be of the form, there is going to be u1 something plus u2 something plus u3 something and this term over here, right. So it will be a plus v1 something equal to 0, right. The second equation is, so this is from your FEM. Second equation is going to come from BI. So what will this have, for example? So again it will have u1 something.
So for the interior triangle,
yeah,
we have the same equation as phi of Ti comma n.
We'll come to that, we'll come to that. Let's just do the bookkeeping of equation 2. Equation 2 will involve all the boundary u's and the boundary v's, right. So it will be u1, u2 and u3 will not appear because u2 and u3 are interior, right. So it will u1 something plus u something else, all of these, but all of them will come because that equation, one equation will involve everything, right. So all of them will appear and v1 something plus all of them will appear. That is basically this equation is equal to E1. So this is my boundary integral.
This is just equation 5 written in terms of the new variables.
Yeah, this is just equation 5 written in terms of new variables, nothing different about it. And equation 6 we did not touch. Okay. So we have put all of these things together. The question was, what about interior triangles? Supposing I have a triangle now that is like this. Okay. So with edges 4 and 5 over here. What happens when I write this equation? So when I take this triangle over here, my equation will have u3 something. So if I test along, let's say, edge 3, what all unknowns will appear, if you remember from your FEM module? Everything that is common to edge 3 will come. So I will get a u3, I will get a u1, u2, u3, u4, u5, but no others will be 0, right. So that's how it will appear. So this, the second part of interior edges does not change at all. It's as you did FEM before, that's how you would do it. Okay. But now when I combine all of these together, what is the overall? Let me write down the unknowns now. Unknowns are going to be, so u and v, let's write it. U in the interior, u on the boundary and v on the boundary. These are my unknowns, right. So this is n plus 2m cross 1. Okay. Now I am going to partition this like this. Three parts. Okay. So the FEM equations, yeah.
The second equation will have m and m variables.
Yes, these are m of them and these are m of them.
First one being h tan, other being u.
The first is u's which are h tan and the next are v's which are ez. Okay. So what do you think will be the structure of this matrix that I have shown you over here? I have broken it up into subparts. So when you take, so for example, the first, these equations will correspond to testing on interior edges. Okay, those are the n equations by testing on the interior. Okay. Will it involve any, so the example which was being asked just now, supposing I take an interior triangle, okay, something like this, and I test along an interior edge. So example 3 is a good example of an interior edge. So the equation for 3 involves u1, u2, u3, u4, u5, correct? That's what I will get. Will there be any V's in that? There will not be any V's in that, right? So, when I look at this equation over here, I will have all the U's, I mean not all, whatever U's are close to it, are associated with it, but the V's will be 0, correct. So, when I write this equation over here, I will have some Ui's, some UB's, and V's will be 0. So, I am going to write a 0 over here, because we are multiply this guy in this fashion with the elements over here. Okay. Think of writing one row of an equation. So, it will have the Ui's and the UB's, but no V's, because these are interior edges. Okay. Then I move to the FEM equations, but considering the boundary edges, right. So, that is the example that we took over here. For example, this equation 1, it involves the U's and the V's. Okay. So, it involves the U's and the V's. So, all of them are non-zero in general. Finally, when I come to, so this is testing on interior, this is FEM. Then I take this is FEM testing on boundary edges. This involves, as we have seen, it involves, if you look over here, it involves U1, U2, U3. U1 is on the boundary, U2, U3 are on the interior, and it involves V1, which is on the, obviously on the boundary only. So, it involves all of these 3 blocks will be non-zero. Okay. So, this is there, this is there, this is there, this is there, and this is there. Okay. Now, we finally come to the remaining m equations, which are from the boundary integral. Okay. Only boundary edges. Which of these blocks will be 0, which will be non-zero? First block is going to be 0, because the equation 2 that you have seen over here, it only involves the U's and the V's on the boundary, right. So, this will be non-zero, is equal to,
So the last line, right?
yeah,
The vertex is basically the second equation.
the last is the second equation, right. Yeah. Which of these entries are non-zero? When I test along the any of the FEM edges, will I get any non-zero term on the right hand side? Look at, for example, equation 1. Is there any right hand side term? There is no right hand side term. And I am left with just the E, which is coming from VB. So, I have a system of equations which is of the correct, I have n plus 2m equations in n plus 2m variables, and now I can solve this. Notice I have put a single tick on some boxes and a double tick on another box. What might be the reason? What does a single tick imply? From FEM, but little bit more. What will be the nature of those equations? Sparse, right. So, single tick is sparse, double tick is going to be dense, because it involves every element, every equation involves every, in my equation 2, every edge is involved in everything. That was the case in the boundary integral, right, surface integral, every edge was involved, that is why my system of equations was dense. So, this is dense. So, what are the, let us just summarize in terms of sort of advantages and disadvantages. I have boundary condition is what happened, I replaced ABC by an exact boundary condition, right. So, it is exact, so that is a great plus point. Okay. Air, do I need to discretize air now? No need. So, my boundary condition, I mean my domain of discretization has shrunk to the bare minimum required. What is the disadvantage? System of equations is larger but marginally. If you take a very large volume and take the ratio of interior edges to boundary edges, it's not much of a price. It's dense, right? So my system of my matrix is no longer sparse. That's a big disadvantage because now I no longer have a n log n solver. But it's not as bad as the if I were to have made the whole thing into for example, if I made the whole thing in using volume integral method, then I'll be discretizing the entire volume into one dense system of equations, right? So it's partly sparse, partly dense. Okay, so I need to come up with a special solver that can exploit the fact that part of the matrix is sparse and part of the matrix is dense. Okay, so there are some ways of doing it. One example is using any guesses? So MATLAB is. Does the word sure ring a bell? Sure decomposition. Is it sure decomposition or sure complement? Sure decomposition was the decomposition we did of a matrix, right? So this is what I'm saying is not sure decomposition but sure complement. Okay, so sure complement splits a matrix into 4 parts, right? So for example, if I were to you can split this using sure decomposition, and inverses of sub matrices are involved. So you can, for the sparse part, use the n log n solver, for the dense part use a regular solver, right? And that's how it is done in the literature. So if you just give this n plus 2m system of equations to MATLAB or any solver of your choice, it's a bad idea because you are not telling the solver to exploit the structure of the problem. In any linear algebra problem, if you can exploit the structure of the problem, you will get big wins. If you didn't tell it, it would treat this as a dense matrix of size n plus 2m, and it will do the whole donkey's way of order n cube, right? So this Schur's complement is one way of leveraging this. I mean, I will not cover it, but you can just look up Schur's complement online. It's not the same. I mean, when you see the Schur's complement, you will realize it's very different from Schur's decomposition.
That complement is the same as that test for positive.
No. Anyway, that is a separate part. The main sort of summary over here is how we managed to combine the best of two worlds, right? So we did FEM, and this is specific, right? I chose a vector FEM. When I chose a vector FEM, my unknowns became the unknowns along the edges.
So one more good thing is we get the EZs on the boundary.
Yeah.
And we get H on it.
Yeah. Yeah, the other advantage, I get EZ and H on the boundary, which is great because where does that directly plug into? When I want to calculate the RCS using Huygens principle, I need E and H. In the FEM, what happened was I got H everywhere, but I need E for calculating Huygens principle. So then I will take an average over 2 elements or something like that. Here I get it.
In the interior, we are still stuck with it.
In the interior, we have only H everywhere, which is good. Actually, if I'm solving a RCS problem, radar cross section problem, I don't care about these n of these values. I don't care about, but I still have to solve for them. What do I do with it, right? Finally, radar cross section depends on field far away. Field far away I write from Huygens principle. Huygens principle only needs the boundary. So I need only 2m of those guys for the RCS, not these n interior fellows. But there is no way to decouple, so I have to solve for everything. So this comes out very nicely in this. The only challenge is to write a good solver that exploits this structure, which is a solved problem in the literature. You just have to look it up. It has been done. Okay. Same principle could also be used if you wanted to write a mode solver to find the eigenmodes of some waveguide or whatever using this approach. There also you will have the same problem. You have FEM for a waveguide, but then you need some air outside of it to apply boundary condition. So why do it? Apply boundary integral. So the idea is what I want to convey, how to cleverly combine change the boundary condition and get it from somewhere else. So, in fact, your commercial solvers, many of your like HFSS and so on, they have nowadays these options inside, either absorbing boundary condition or boundary integral. So, now you know what they are doing inside. Okay, so I think that brings us to an end of hybrid methods. Yeah.
Like, can we can use this for eigenmodes as well?
Yes, you can use
But
this.
then here we have an incident field, right?
Yeah, so to use it for an eigenstructure calculation, you would actually have to go back to step 1 itself. Step 1 itself is where you will have to put in your h to have a e to the j beta z and start. So, you will follow the same idea, but you will have an extra beta squared term hanging out everywhere, which you have to deal with carefully. If you deal with it carefully, same recipe will hold true. Because what we have finally done is we have just modified the boundary condition.
So, but then we use the surface integral equation, right?
Yeah.
The existing theorem.
Yeah.
There we had an EI.
There you have it. Yeah, so everything has to be done carefully.
So for that also I have to put the beta square. And
Of course, everything has to be changed if your problem changes, right? If you have a waveguide problem whose modes you want to calculate, there is no E incident.
So this is basically you are able to calculate the incident field in the computational domain. or
Yeah.
you can calculate R.
The total field in a computational domain is what we are able to calculate by doing all of this. No, so this is along the overall boundary. We had actually worked it out when we write it for each element, these terms cancelled off along the individual boundaries, and you were only left with the outermost boundary that did not cancel. See, at this point FEM has actually not come in. We had applied which theorem? We had applied your divergence theorem to convert one surface integral into a one area integral into a line integral, which is why the right hand side became a line integral. So, this is true only on the boundary. So, Ti is going to be for an interior edge is going to be 0 on the right hand side. If I is an interior edge and I am testing along that, only the left hand side is 0, right hand side is 0.
So third basically just shows the boundary condition.
Third is, say again?
Third is just the boundary condition.
Third is the boundary condition on the right hand side. The left hand side is still the LHS A matrix, right? That's going to give you your A matrix. Ax is equal to B. So, I don't want to go more into how what the Schur complement is, but it basically, instead of right now what we know is given Ax is equal to B, how to solve it. Schur's complement on the other hand breaks up A into, let us say 4 parts. Okay, so let us say A, B, C, D. Okay, and then you write your split your variables also as x, y, and let us say B1, B2. Okay, and there are certain formulas which allow you to write the final solution in terms of A inverse, D inverse, and so on. So, you do not have to take the inverse of the whole thing. So, for A inverse, for example, A might be the sparse part. So, its inverse is easy to do, right. So, those are the kinds of tricks that Schur's complement does.
So one of them can be a 0 block.
One of them can be a 0 block and so on. Right. So, this is, I mean, this is pure linear algebra. Okay.